I really encourage you to participate and look for summer internship or co-op and so forth. So as such, I let you out early. How's that? 2 minutes. Yeah. No, I think it's important for you to get some related job experience. Right. So Christmas has been graded. You see your score. For those who didn't get a 10, I really need to alert you that if you cannot do that quiz, you are in a lot of trouble for the test. Right. So I have very little feedback from you. And I don't know what level you are at, and I don't want the test to be a surprise to you. So I don't know if I'm repeating myself too many times. So all the homework that we are dealing with that due today, which you need to upload, and the next 2 lectures will be in the test, and that's the minimum. That means that if you can't do them, you cannot do the test. Okay? So I think Mike is available to help you for any office hours, questions, and so forth. The test, I will post some practice problem for you. Maybe after Thursday lecture, you can work on that on your leisure. I don't know what else. I may schedule an evening help session on Tuesday, but then you have class on Tuesday as usual, class on Thursday as usual, quiz on Wednesday. So it's going to be very busy with next week. Anyone who would think a study session on Tuesday evening will be useful. I mean, will you show up? Yes. Okay. I will schedule and let you know where. But the test is going to be in this building, not this room. And please pay attention to the announcement and the posting on Canvas. Some of you still don't know what the O mean in the homework assignment. What does the O mean? Huh? The old edition. So we will be very. There's no mercy in the quiz or in the test. You don't follow the instructions. We just don't give you credit. All right? I mean, the test is very well spelled out. You don't put any of the question on the, you don't put any answer on the question sheet. The question sheet is collected separately, and then you do all the work on some work paper that will pass around. So if you don't follow those instructions, we won't have any mercy for you. All right? I'm being harsh, but I need you to, you know, you're all junior. I think you're at this stage very well prepared to tackle any of these. So the test is going to be the same time frame as the lecture, hour and 15 minutes. All right? So we'll have more about that on Tuesday of next week. So agenda is I'm trying to slow down because this is where you should have a lot of questions. If you don't, again, I have no feedback. I have no idea. And I'll make the test very difficult. So I assume you all know the stuff and you are on top of everything. So it's to your benefit to ask questions. Yes?
Will there be a practice test available?
Will there be a practice test? Yes. I just said I will have post some practice problem. By that I mean practice tests.
Okay,
They are the level and length that you would think will be good preparation for you for the test. Yes? Yes?
Can you go over the last question of homework that we just turned in today?
Okay, so you want to go over the homework problem for today?
Yeah.
Which one? I have them listed on my agenda. That is my intent. Yeah, so when we get to that, we'll definitely. Any question you have, I'll slow down. But if you don't ask me, I'll keep going at full speed. You know, taking my class, like I said before, maybe not in this class, it's like drinking water from a fire hydrant. Right? Yes?
Yeah, when we're doing the momentum equation and we add the pressure times the area,
yes,
like those have directions, correct?
Yes, absolutely. Okay, so the question for those who didn't hear is, on the left-hand side where the summation forces, all right, there's the pressure force, which is the surface force, which consists of a pressure gauge times an area. All right? Does that have a sign? You bet. Right? Momentum, force, it has direction. Yes, absolutely. Very important. Okay? Now, those are the questions that you should be clarifying. Now, when I say I use gauge pressure times the area, what am I neglecting in terms of the ambient pressure? Why am I neglecting the ambient pressure? Why am I using the gauge pressure? You understand my question? I'm not posting my question very well. I use the gauge pressure because the ambient pressure cancels out all around my control water. Right? So those are all the very little detail that you should get them all clarified by now. Yes?
How similar is the practice test to?
How similar is the practice test to the actual test? I can tell you they're not the same. Yeah, that's the true answer. In terms of level of difficulty, similar. Right? But it will be always, the test will be always a grade beyond your homework. It will be more difficult than your homework. If you don't look at the posted solution, Maya and I just consulted, everything on this canvas is up to date. If you don't look at it, there's no mercy on you. Yes?
What do students typically mess up on the first time?
Sign. What the question is for those in the back, what do students typically mess up on the first test is the momentum equation. The sign. All right. Now, I hope I have beat on you enough on the G sub C. The other problem, some of you have half a dozen, is missing a factor of 30. Okay? Other question? Yes?
Did you say that there's solutions posted for the practice?
Yes, the solution will be posted for the practice problem. Yes, it's all self-contained. You can work at it at your leisure. You don't have to work on them. You can ask those questions during the study session, but they are such, the solution is given, you can find out yourself whether you have done it right or not. Right? Yes?
Are we expecting to memorize all the equations?
No. You don't have to. Why? You have a formula sheet. You are allowed to have half a page of formula sheet. Right. But that's a safety blanket. It is, you know. Other question on the formula test? Yes?
You mentioned how many questions will be on the test?
How many questions on the test? I don't know. I haven't set it up. There are always some work problem, not your homework, but there are also short questions, you know, not your quiz. Right? So it's a mix. It's a mix. So the agenda today is go back to the 2D play problem. I kind of watched through the end, and I asked you specifically to look at the y direction momentum equation. I hope you have done it, because that's very important practice and foundation for you. So I'm just making myself available for questions. Then I'm going to revisit, by way of the homework, on that non-uniform parabolic velocity profile in the pipe. And we're going to deal with that in chapter 8 in a month. Flow in the pipe, how do you estimate the pressure loss? And I would like to revisit 2124 by way of viscosity. Very quick, because you know that. I just want to, at the right time, to use that problem to, you know, revisit that concept and set the stage for future lecture that is to come. Then I would answer any question on the old homework. So there you can ask me anything you want for both problems due today. And then I will spend a little time on new homework. Same thing, XY momentum continuity. And then we're going to start a new topic, but it's something you have seen in 2124. That's the Bernoulli. And that's chapter 3. And that will be in the test. And there will be homework both today and the next two lectures dealing with Bernoulli. So that's the agenda. Homework assignment is reading on chapter 3, going back to Bernoulli, what it is, how to use it. And the homework is 3 hours, maybe less, with the discussion we have in the lecture. And the last set of homework before test 1 is also posted, and that will be collected on Tuesday before the test on next Wednesday. Question on any other logistics? Yes?
Is the material we cover Tuesday going to be on the test?
Yes, everything on Tuesday will also be responsible for in the test, correct? Yeah. So Tuesday, what we will do is I may spend half the lecture just answering questions relating to test 1. And of that half lecture, I may spend the first 5 minutes to give a big picture overview of what we have covered in terms of the key concept, important equations. But that's it. I won't have anything formally to structure to talk about. And if you have no question, I will continue to lecture. So you may come in and prepare a list of questions to slow me down on Tuesday lecture to your benefit. Yes?
Is any of the solutions for Tuesday's homework pre-posted before the test?
Yes, every homework, I'm repeating myself, and Mike been doing that. Right after the lecture today, the solution for today's homework should be posted. If that didn't happen, you will let me know, and that might know, and say, I need the solution. Right, so for Tuesday, it's the same. So it should be available for you to study. Yes?
Who's the which homework does the test cover?
Okay. From first lecture to this last set, which is still Wednesday, sorry, Tuesday of next week. Other questions? Okay, the floor is open for question on this 2D plate problem. And I would wait for you to ask. First, do you understand the whole layout, the geometry of the problem, 2D versus axisymmetric? Any question on why the pressure force completely disappeared? What does it mean in the free jet? What does that mean to you? Any problem? Or even if it didn't say it's a free jet, it's just a jet coming out from a water hose. So in this case, a jet didn't say water or air, a jet coming out from a 2D nozzle, but it's emptying into ambient. What does that mean to you in terms of the pressure in the jet? The problem didn't tell you anything, but what do you have to assume? The pressure inside the jet.
Atmospheric.
It's atmospheric, okay? So any question on any of those? And you understand why on the plate, because it's frictionless, there's no shear and the forces along that plate, parallel to the plate, is zero. Okay? Yes?
My question is the velocities coming from the jet as well as coming off the top of the plate and off the bottom of the plate. All the velocities here are specified as equal.
Yes.
Would that be something that is specified in the problem or
Yes.
something that we need to assume?
Okay, for those who didn't hear the question, in this problem, you were told, just an other problem, as well as in the quiz, you were told the velocity everywhere is v, same everywhere. That will be told to you in the problem statement. After Bernoulli equation, after test 1, you're going to find out you don't need to be told. It turns out it's the consequence of the Bernoulli equation, but we'll hold on to that until later. But at this stage, yes, you will be told. So you were told the problem statement say everywhere 1, 2, 3 station velocity is v. What else on the problem statement? Okay, so you understand the use of the X momentum equation? Happen the pressure is all cancelled, so you don't have to deal with the sign of the pressure, but other problem you are not that lucky, pressure has to be accounted for. Okay, any question on the Y momentum equation, which I didn't cover? You want me to go over that? Okay. So we are at this point, last time. So I'd like you to help me and read to me how this Y momentum equation on the right-hand side, that's what we are dealing with. The left-hand side is already taken care of higher. We look at all the forces. And now what we're left with on the Y momentum equation is simply m dot v out being positive and m dot v in being negative. What is the name that we give to m dot times the velocity? Momentum flux. Yeah. Momentum flux. So those can be a question for you in the short question. What is that term called? All right. So m dot, once again I'm repeating myself, does it have sign? No, it's a scalar. It's rho VA, as long as velocity and area is perpendicular. And we choose our control surface very intelligently so that they are perpendicular. So the m dot in this case at station 2 is simply rho v times h2, which is a height. And it's not an area, so am I missing something? What is that second dimension? It's the depth, which is 1. All right? So we did that in the X momentum equation. I'm just repeating myself. There are 2 stations going out, exiting, 2 and 3. One go up the plate, one go down the plate. Same token, rho VH3, positive. Positive. because they are out momentum flux. No sign. Don't double count and don't confuse yourself. Do you get it? Then I deal with the velocity, which is a component parallel to the which direction? Y. Sign or no sign? Do you care about the sign? For V? You bet. Why? It's a vector. Sign is important. Okay? As such, what we have for V2 and V3, because the coordinate is chosen to be parallel and perpendicular to the plate, they're both zero. Again, by choosing an appropriate coordinate, I make my life, as you will see later on, much, much easier. Okay? Any question on the exiting or out momentum flux? Can you do the in momentum flux, which is always carry a minus sign? Can you do that? Okay. All right. Problem is done. Any question? The rest is algebra. The rest is just bookkeeping. The mechanical engineering part stops right here. Other questions? Yes.
I just, I'm a little bit confused on where the H is coming from.
Okay. Let's go back to the problem statement. Nope, not this one. So first, we drawing the diagram again. This is a 2D problem. That's the nozzle I'm dealing with, as opposed to a previous homework example where it's circular. This is axisymmetric, this is 2D. So the height h is simply, at station 1, the height of this 2D nozzle. At 2 and 3 is the height of the sheet of jet, say water, going along the plate. Right? The second dimension is into the paper. And we take that as unity per unit depth. This type of 2D problem will be used many more times for the rest of the semester. So if you have questions mentally how it should be pictured, please ask now. Okay? Anything on this plate problem? You cannot do your homework until you have full understanding of how this problem is solved. Questions on this problem? So anyone wonder what happened if you don't listen to me and you just say, I'd like to do a coordinate system that is more conventional? A coordinate system that's more conventional would be what? This is what we did. This is a conventional coordinate system. X horizontal, Y vertical, right? So it's always good to challenge your professor because I'm not always right. If you were to do that, this page 3, or rather page 4, the last page of the handout, show you how the X and Y momentum will change because of your new coordinates. And just to set up the two equations, the algebra on the right, as you can see, there's a whole lot more involved. Because no longer is the coordinate y taking advantage of the fact that the velocity is 0 in the y momentum equation. This is just setting up the xy momentum equation. Then there's about 1 hour of algebra in this 3 dot dot dot, so that you arrive at the same answer. if you don't make any mistake. So what's the takeaway?
Take advantage of the exit.
Always listen to your professor. That's a joke. Okay, so that's it, all I want to talk about on this plate problem. Any other question? All done? Clear? Because I'm going to turn this projection off. All right, very good. All right, let's go back then to more uniform velocity. So I have a problem like this given in the test several years ago. Whether I will use it again this time, it's not known yet. So I just want to go over the solution very quickly. I have given a lot of hints last time, so I hope with that you're able to solve the problem. If not, you can ask me again. After that, I'd like to revisit the concept of viscosity. So the velocity distribution given in the problem statement is a parabola in terms of the radius. Oops. R is the radius, this is the center velocity, which is the maximum. So if you look at continuity, the part that I've shown you, you'll find that the average velocity happen to be half the maximum velocity. Can you do that? Can you do that integration? If you cannot, ask now. I've given you how to formulate the differential area and all of that. Any question on that? Or everyone is on top? Yeah.
Is that for any parabola?
What do you mean?
Or
Any
is it like
parabola,
only
that's
second
that's
degree?
correct. It is for any parabola. Well, this is one parabola. I don't know. I can answer that.
Okay.
I can answer that. If you change the parabola, will this change? It probably will. So it's not any parabola, but for this particular parabola, yes. Fair question. Yeah. So I can see if the parabola is more like this. You may have a different answer. I don't know until I integrate it. That's the fair way to look at it. All right? Yes?
Could you go through the integrations?
Okay. So do you understand the differential area that we pick, which is a strip of 2 pi r dr? That's my differential area. Do you get that? Yes?
So how do we know for each area that we're given what to pick as a differential area?
That's the problem-dependent answer.
Okay.
A circular pipe, this is very common. So there are not many different shapes in our engineering analysis. A 2D plate, you have seen it, right? So the hydraulic jump which is 2D. Anyone remember how we picked that differential area? This is y. It's dy, which is the length. I need an area. dy is times what? Times f, which is 1. That's my differential area. For a 2D problem, for a circular pipe, as it's symmetric, that's your differential area. Those two cover most engineering applications, if not all. So you see it once, you see it all. Okay? So do you understand this? So with that, the integration I won't repeat. Solution is posted at the end of the lecture. If you go through continuity, you will prove to yourself that at the end, when the algebra is done, this is what the average velocity look like. And what it is then, I can pretend, instead of having this diagram, for simplification of my analysis, instead of dealing with a parabolic velocity profile, I can pretend or hypothesize, which is saying this is not the true velocity. Velocity is always zero at the wall, but if I were able to pretend the velocity is uniform now, I have this average velocity which happens to be half my maximum velocity. And then I can use this to solve problem based on continuity. That's what we have done, right? Do you get the essence on continuity alone? Because if you do, then I can go on to momentum, which is an extension of this concept. So instead of integrating the profile like we did for this problem, I can, for all intent and purpose, say the mass flow rate is equally given as rho times the area times the velocity. What would that velocity be if I don't have to integrate? UC over 2 or UF, right? And now we get the same mass flow rate. Okay? Any question on this? Yes?
Does the shape of the parabola change with the fluid? So like, if I have a pipe of water versus a pipe of like maple syrup?
Yes. The answer is yes, it does. Yeah, we'll study more of that in internal pipe flow. And this is what we call a laminar flow, parabola. But most flow in nature is turbulent. And the parabola doesn't look like this. It doesn't become a parabola. But the main message is that the flow is by far not uniform in real life. It never is uniform. Because the velocity has to be zero at the wall. That's just something you need to remember as an engineer. But we simplify it because then it's more trackable, more doable. All right? Momentum is the same thing. I don't want to drill on this too much. The hints that I gave you last time is to say the momentum flux for the non-uniform case based on the momentum equation can be obtained by this integral. So we can draw a parallel between that and continuity. The only addition is now I have another velocity inside my integral. And at the end of the day, when all that algebra is done, what we learn is that the momentum flux for non-uniform flow which is this integral, I let you do the algebra, is actually 30% higher which is fairly substantial, 30% higher than if you assume the velocity is uniform, and based on that, you obtain a uniform momentum flux based on this so-called average velocity. So the solution is there for you to look at and digest. But now what I'd like to do is use this example to revisit the concept of viscosity and do it relatively quick. Prior to that, this is again a repeat of 2124. Anyone first tell me the difference between a solid and a fluid? Solid. Anyone has a book with you? Can I borrow a book? Can I borrow this book?
Yeah, of course.
So solid, a block of aluminum, or a block of stainless steel, or this book, when you shear it, which means you apply tangential forces top and bottom, what will happen to the bolt? So I shear it. It's probably not a very good illustration. But if I shear it, if I have a foam bolt and I shear it, you never know what foam bolt looks like, right? We don't use foam bolt anymore. So if there's a bolt, if I shear it, what will happen to the originally rectangular shape? I'm trying to demonstrate the best I can. It shifts, it deforms and becomes from a rectangle to a parallelogram. But eventually it stops. It reaches static equilibrium. I cannot shear it anymore unless I break it. Right, that's solid. That's solid. And remember modulus of elasticity? All those relate to the deformation as relate to how the shear is being applied. All right? So all that is your static, deform. Fluid, air between my hand, or a sheet of oil, or water, two plate, I shear it, will it stop? No. It will forever continue to deform. Nothing will stop it. That's the difference. Just that small subtlety. And that itself makes it a whole different study, all by itself, and it's a major one in mechanical engineering, and more so in aerospace engineering, right? So this is what we try to capture by way of shear stress, or what we call viscosity, which can best be illustrated by this simple cartoon. It's not physical, but it's very helpful for us to understand the effect of shear on a fluid. So it consists of two parallel plates with a fluid trapped in between. It can be oil, can be water, could be air. The bottom plate is stationary, the upper plate is tacked along at a constant velocity v. And to make that happen, I have to apply a force F. And we assume, for simplicity, the velocity in x direction is linear. It's linear. And with this simple presentation of frictional effect within this plate, out comes the definition of viscosity, which is the shear stress, which is force divided by area of the plate, is equal to, the proportionality is now changed to the fluid property of so-called viscosity, and the velocity gradient, meaning v, gradient, something divided by length, v over h. That's how viscosity is defined. All right? Yes?
Is that a negative sign?
No, this is definition. It's a triple equal sign. That's the equal sign. But when I have a triple one, that means it's the definition. That's how we define viscosity. Right? Have you seen this before? 21, 24, very good, okay. Now with the new twist now, just to take it to the next level, the velocity inside a plate or a pipe is not linear. A more physical representation is that it's parabolic. So we go on. Okay, the profile of velocity, they actually look like this. And you understand why at the bottom velocity is 0 and why at the top the fluid velocity is v. We call it the low slip condition. So now, moving forward, which we'll revisit at the end of the semester, when we talk about boundary layer, the viscosity is more correctly and appropriately defined as a partial derivative, because the velocity is not linear with respect to the distance y. So that's just a quick recap of what viscosity is, how that frictional effect will affect some of our analysis. But having said all of that, at least for test one, we're going to deal with mostly uniform velocity to simplify the problem. But with the homework that you have seen for the hydraulic jump and this problem, you are equipped, or at least knowledgeable, to understand that in real life, they are not uniform. Right? And that's the message I want you to remember. Any question on this particular homework and the concept of viscosity? Yes?
Can you explain again what the three variables are?
Okay. So I'm mixing my nomenclature, which I can see why people are confused. So first, this symbol mu is what? Viscosity. Then I move over here. Vx is the velocity in the x direction, which we have in many other problems use the symbol u to represent. Y is the coordinate vertical away to the plate, and x is parallel to the plate. So what I'm looking at is the gradient. dvx, dy, that's at each point the gradient. And that will define the viscosity. This tau is what? Shear. And how is that defined? What is shear stress? Force over area. Yeah. So it's somewhere here. That's what we call the shear stress. H is the height between the plates. Any other question on any of the nomenclature? Anytime. Yes?
How would you find the A, the area value, if you were given?
It's given.
Okay.
Yes, I have to give you the geometry of the plate and the force it takes to maintain the constant velocity of the plate, no acceleration. All right, so that's the set of the problem. All right, two plate, the upper one has an area and applying a force, so it goes at constant velocity, no acceleration. So the force F is just enough to overcome the friction, right? Because it's a fluid and it's not static, solid, it will continue to move. It will never become a static deformation. Okay, so the modulus of elasticity and all that become somewhat irrelevant. We have to redefine a constituent equation. So as an example, is to parallel this to the solid mechanic discussion you have in ESM. So if this is a class in static, instead of viscosity, what we have, first of all, stress and strain. I have a block of aluminum. I'm applying normal stresses, not shear, will come later. And the block deform statically. Anyone remember all this symbol? Tell me. Normal stress, which is what divided by what? Force divided by area. The epsilon? Strain. Dimensionless is how much it changed, delta, divided by the original length. And E? Modulus of elasticity, which is a property of the solid. You have to look it up, whether it's stainless steel, aluminum, or a block of wood, they're all different. Same with fluid. You know, you have different viscosity for water, different viscosity for different oil, 10W40 versus 10W30, etc., etc. It's a property of the fluid. So this is modulus of elasticity. Okay, remember all this? So what happens if I apply shear in deform? What happens to that block? It becomes, like I said earlier, a parallelogram. But it will be static, statically deformed, and then it will stop. And the constituent equation here is the shear. And this G is the shear modulus of elasticity. I don't think you remember this, but not a bad time to revisit it in parallel with what you see in fluid, and this is all but a revision, review of 21, 24. Okay? So that's it. I mean, I just want to make sure you understand how the shear viscosity play a role. Any questions? Are you ready for the, yeah?
When you have a v sub x equals v, what is the y and h? H is the height, but what is the y referring to?
Well, okay. So I have a coordinate system here, which is x coordinate parallel to the plate, y coordinate normal to the plate. So that y is the coordinate y. Did I answer your question? So this is y is the distance measured from the plate. Okay. So the velocity is linear. 0 at the wall. When y is 0, I have 0 velocity. When y is h, what is that velocity? V. And that's what this Vx is, which again, with my other nomenclature. So Vx is nomenclature we will use just as many times as the small u, moving to a 3D problem. Vy will be equally usable compared to the small v. Both is the velocity parallel to the y direction. Okay? Are you clear of the nomenclature now? Yes?
Is the V in the shear equation, is that the velocity of the top plate in relation to the bottom?
So I have velocity at the top plate, which is a constant, v, 10 feet per second. I'm taking that plate with a force of 10 pounds and it's moving at 10 feet per second. Those are all constants. This Vy, which is the velocity inside this layer, it goes from 0 to 10 feet per second in a linear fashion. 0 at the wall, half in the middle, maximum at the top. Okay? Does that make sense? And same with, if the profile is not linear, it becomes a parabola, like the pipe problem, but the same nomenclature. Okay? Other questions? Okay, so homework today. There was a question about the homework due today. Can you ask that question now? Which one?
You talked it already.
Oh, this one? Okay. Yeah, I skip a lot of detail. There are a lot of algebra on the momentum, but I'll let you look at the solution first. If you still have problem next on this Thursday, ask me again, please. All right? So the floor is open for the two other homework due today. Problem 38, the elbow turn 45 degrees. In the area, yes?
So in the problem statement, it said that the flow is not frictionless.
Yes, very good question. Why is that needed? Let me just touch on that. So the problem itself, I hope it's quite doable. 2D momentum. And this is setting the stage for next couple set of homework. Where in this problem, a pressure gauge is hooked up to the upstream section of the pipe and it with 10 psi gauge. Right? So first of all, can you do this problem with what is given? Any question you have to go over? Continuity, x momentum, y momentum. Very good. Okay. Sign is not a problem. Pressure, force, you can deal with all of that. Everyone is square. Okay. So the frictionness, which I purposely avoid talking about last time. You are told that this is not frictionless. Let me throw the problem away and change it completely. I will tell you that assume implicit. Assume implicit, but because of that assumption, I'm going to take this away. I'm not going to tell you what the pressure upstream is. Can you still do this problem? And how? You have only x momentum, y momentum, and continuity as of now in the original problem, right? And you did it with a given upstream pressure. Now I take that pressure away from you. But I'm going to let you make an assumption and pretend the flow is frictionless. So I have frictionless, steady flow, right? What else can you think that may click in your head? Along a streamline, incompressible because it's water, right? Let me listen again. Steady flow, incompressible, along a streamline, and then I was told it's frictionless. What should click in your head? What should turn on? Bernoulli's equation, which you have in 2124, which you will need now to do the next set of homework. Right? So maybe it's a good time for me to take a moment to talk about Bernoulli first, since it's so tiny. So I'm going to diverge to just quickly revisit Bernoulli in the context of what we talked about. So we're just going to focus on the application of Bernoulli prior to test 1. And then after test 1, we're going to do a deep dive and